Hello, ladies, gentlemen, and in between, and welcome back to another episode of Maths with Hamblin with your beautiful host, Hamblin. And today, my boys, we're going to be covering intersecting curves. Okay, so the meat of today's lesson is when we've got two separate curves in the xy plane. For example, here we've got a parabola and a line with two different equations. How can we figure out the points, the exact coordinates of the points where these two curves intersect each other? And that's an interesting problem, right? And it could be useful, who knows? And we're going to assume that we know the equations of both of these curves, because if we didn't, that would be pretty hopeless, right? How could we even start? Anyway, so assuming we know the equations of both of these curves, how can we figure out the coordinates of the intersection points? Well, first of all, let's just recap on what it means for the equation of a curve, what that even means. This parabola has equation y equals x squared minus 3x plus 10. Recall that that means for every single point on the parabola, including the intersection points, that the coordinates of those points must satisfy that equation, i.e. that y equals x squared minus 3x plus 10, and the exact same thing goes for the line with its equation here. Now, how can we use those two equations to figure out the intersection points? Well, if you're clever, here's something you'll realize. Let's say that this intersection point here, I'll draw a little dotted line, has x coordinate x1 and y coordinate y1. Now, the key thing to notice here is that this point is contained on the line and also on the parabola here, because otherwise it wouldn't be an intersection point, right? So that means that its x and y coordinates satisfy both of these equations, i.e. y1 has to equal x1 squared minus 3x1 plus 10, and also 4 times y1 minus 2 times x1 must equal 5. Okay, so now we've got two equations and two unknowns to work with. This is going to be great, right? So let's write this down. We've got y1 equals x1 squared minus 3x1 plus 10. I'll make that a little bit clearer. And we've got that 4y1 plus, sorry, not plus, that's a minus 2x1 must equal 5. And now what we can do here is notice that we already know what y1 equals. It equals this, so we can substitute y1 there, and we can solve for the x coordinate of the intersection point. And you might ask, but hey, there's clearly two intersection points, but we've only got one equation. Well, as you'll notice, when we sub this in, we'll get a quadratic. So we'll actually get two solutions. So we'll get both of our our points of intersection, sorry. So in other words, that is the general method we're going to use. We're going to substitute one equation into the other to solve for the intersection points. Anyway, let's have a go at a question like that. Okay, so let's take a look at this example problem here. A parabola has equation y equals x squared plus 3x minus 17, and we're asked to find the coordinates of its intersection points with the line 2y minus 10x equals negative 4. Okay, so let's go about the exact same method that we discussed previously. We know that the y coordinate of the intersection point must equal this nonsense, and we also know that the 2 times the y coordinate minus 10 times the x coordinate must equal negative 4, so we can sub in this expression for the y coordinate. Okay, let's do that. So using this equation here, we get that 2 times x squared plus 3x minus 17 minus 10x equals minus 4. By the way, you could have also rearranged this to get it in the form of y equals blah, 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 and then set x squared plus 3x minus 17 equal to whatever comes out of that. That's also totally okay. I've just chosen to do it like this because I think it's just a little more clear. Anyway, let's solve this now, solve this quadratic. So expanding this out, we're going to get 2x squared plus 6x, and then minus double 17, which is 34, sorry. Then minus 10x, that has to equal negative 4. Okay, let's do some simplifying. 2x squared, and then we've got a plus 6x, and then a minus 10x. That is the same thing as minus 4x. And then we've got a minus 34 on this side and a minus 4 on this side. Let's add the 4 on both sides so we can get a 0 on one side, because then we can solve the quadratic. And that will land us with minus 30 equals 0. Now, what's nice here is we can also just divide everything by 2 to reduce the quadratic a bit, make it a nice little bit more simple. And that will also make sure that the coefficient of x squared is 1, which if you know anything about solving quadratics, that's always handy. Dividing everything by 2, we get x squared minus 2x minus 15 equals 0. And now we can choose to solve this either with the quadratic formula, completing the square, or factorizing. I'm going to do factorizing because you can notice that this quadratic can be factorized as x plus 5 times x minus 3, and that still equals 0. And then we know from this that the solutions for this must x equals negative 5 or x equals 3. So that means that the x-coordinates of the points of intersection with the line are x equals -5 and x equals 3. Okay, that's fantastic. I'll meet you on the next bit of the whiteboard to finish off the question. Okay, so we know the x-coordinates of the intersection points being x equals -5 and x equals 3, which means we're halfway there. But how are we going to get the y-coordinates? Well, pretty easy solution, am I right? We can use either one of these equations, really, but I'm going to use this one because it's I'm going to use this one because it's a little bit... I'm going to use this one because it's simpler. It doesn't have a squared in it and a -17 and all that horrible stuff. Anyway, so we can sub in x equals -5 and x equals 3 to this equation because we know that the points of intersection must lie on this line, meaning that the coordinates of the points of intersection must satisfy the line's equation. So we can sub in the x-coordinates and figure out what y-coordinate has to be. So in other words, we can say 2y, oof, this whiteboard pen isn't loving me today, minus 10 times -5 equals -4. Okay, fandabby-dozy. That's the same thing as 2y plus 50 equals -4. Then we can subtract 50 on both sides. We'll get 2y equals, okay, -4 minus 50, that's -54. And then we can divide both sides by 2 and get that y equals -27. So when x equals -5, y equals -27, we have our first intersection point, -5, -27. Fandabby-dozy. Now let's plug in x equals 3. So from there, I'm going to rub out this bit. From there, we can get that 2y minus 10 times 3 must equal -4. Okay, fantastic. Usual business. 2y equals, that's -30. Add it to both sides, we get -4 plus 30, which is positive 26. And then divide both sides by 2, you get y equals 13. So our second intersection point is x equals 3, y equals 13. And boom, there are the coordinates of the intersection points of the parabola and the line. Fantastic. Okay, on to the next section. Okay, so in this next part of the video, I'm going to demonstrate a technique which you're going to use quite a lot to show that curves, to show that two different curves do not intersect or only intersect at a certain number of points or whatever. And that is to use the discriminant. And let's see how we're going to do that. And I'm going to show you how to do that using this example here. So imagine you're faced with this horrible question here. Show that the curves y equals 2x squared minus x plus 20 and y equals -x squared plus 3x minus 10 do not intersect. Okay, how can we possibly show that the two curves don't intersect? Well, I mean, there's nothing stopping us from trying to solve for the intersection points anyway, so if we try and do that, something has to break, right? Surely something like there's a divide by 0 or something must go wrong. So let's try and see what happens, and then that maybe can help us show that there cannot be points of intersection. Okay, so let's try that. So we've got y equals this and y equals that. So if we want to solve for the points of intersection, we know that both the y-coordinates and the x-coordinates must both satisfy these equations. And since we've both got just y equals on both sides, we can just set them equal to each other, right? So we can say that 2, bad pen, minus x plus 20, 2x squared minus x plus 20, has to equal -x squared plus 3x minus 10. Okay, fandabby-dozy. Right, let's try and solve for the x-intercept. So we're going to need to get an equals 0 on one side so we can solve it as a quadratic. So we're going to move all over this to the other side. Moving the x squared over, we get 3x squared. And then subtracting the 3x, we get minus 4x. And then adding the 10, we get plus 30 equals 0. Now, still nothing obvious is screaming out on us on why this can't happen, right? I mean, surely it's a quadratic, there has to be solutions. But that's the key. If there are no points of intersection, then this quadratic must not have any solutions. Because if it did have solutions, then that would imply there were points of intersection. But how do you show that a quadratic has no solutions? The discriminant. If you remember, the discriminant is what determines whether a quadratic has solutions or not. If the discriminant is negative, there's no solutions. If you don't remember what the discriminant is, you can watch a video online or one of my videos. Anyway, so let's calculate the discriminant of this quadratic and show that it's negative, less than 0, and therefore there must be no solutions and therefore no points of intersection. Okay, so doing the discriminant is b squared minus 4ac. In other words, this squared minus 4 times this times that. So negative 4 squared is 16. And then we do minus 4 times. Okay, 3 times 30. Now, do we really have to do any more work here? I mean, 16 minus, that's going to be 12 times 30. That's definitely negative. That is very negative. So this quadratic here, we've shown, definitely has no solutions, which means that there cannot be any points of intersection. And that is how you approach questions like this, where you're asked to show whether two curves, how many points of intersection there are, whether there's none, whether there's two, or whatever like that. And you can also use this as a tool in order to solve harder problems, which I'm going to show you right now. Okay, so this second problem is just a little bit harder. I really like it. It goes like this. Find the values of m such that y equals mx is a tangent of the curve y equals 3x squared minus x plus 3. I mean, how that is, I mean, how would you even approach that? That doesn't even seem related to points of intersection, but it actually is. But to see why, let's break this problem down to see what it's fundamentally asking, right? So, first of all, we've got y equals mx. Okay, what is that? Y equals mx gives the equation of a line that goes right through the origin with gradient m. So as we vary the value of m, we'll either make the line steeper, shallower, more negative or less negative by varying the value of m. And we need to find the values of m, so the values for the gradient of this line, such that it's a tangent to this parabola here. So what does it mean to be a tangent specifically? If I was to draw out this parabola, say, and then let's just say that's the line y equals mx, we know that this is what a tangent looks like, but what's the defining property of a tangent? Well, it's that it only just comes in and just kisses the curve and then moves back out again. It only intersects the curve at one single point. Okay, that's brilliant, right? Because that means that when we set up the equation to solve for the intersection points, there should only be one solution. So that means we can use the discriminant again. Okay, let's go and do that. So, solving for the intersection points of the curves will go something like this. Because we've got a y and a y equals on both sides, we can just set the two equations equal to each other. So 3x squared minus x plus 3 has to equal m times x. Okay, fan-dabby-dozy. Let's subtract the mx over to get an equals 0. And then we'll get 3x squared minus x minus mx plus 3 equals 0. Okay, yeah, that quadratic's nasty, and there's an m in there, so we can't even use the quadratic formula to get solutions, but we can still use the discriminant, and I'll show you how. First of all, let's factor out this x here as such, so minus x, and then that's times 1 plus m. That seems wrong, I know that seems wrong, but just distribute negative x and you'll arrive back at this. And what I've done here is I've found a quadratic in the form 3x squared, so a number times x squared, minus a number times x, and then plus 3. So we've actually got it in the standard form. It's just the value of the b coefficient, so b, is negative 1 plus m, which is slightly annoying, but, you know, doesn't really matter. Anyway, so what do we know about this quadratic? What it must satisfy? Well, if we want y equals mx to be a tangent, we jolly well hope that this quadratic only has exactly one solution, no more, no less. And that occurs when the discriminant is exactly equal to 0. So we can set up the equation that b squared minus 4 times this times that must equal 0. And that will give us an equation for where we can solve for the different values of m. So let's do that. So what's b? B is negative 1 plus m. So let's do that. So negative, can barely see that, negative 1 plus m all squared minus 4 times 3 times 3 must equal 0. Okay, fantastic. Negative 1 plus m squared, that's the same thing as 1 plus m squared, and I'm just going to keep it like that. I'm not going to expand it, because that will actually make it harder, as you'll see in a moment. And that's minus 4 times 3 times 3, that's 4 times 9, that's 36, equals 0. And now, this is why we shouldn't expand it, because it's actually easier to just add 36 on both sides and then take the square root. So let's do that. We'll get that 1 plus m equals plus or minus root 36, so 6. So 1 plus m either equals positive 6 or negative 6 in order for the discriminant to be equal to 0. So that means that the different values of m finally are m equals, well, okay, if we choose positive 6, then when we subtract 1, we'll get 5. And if we choose negative 6, we subtract 1, we'll get negative 7. There we go, fan-dabby-dozy. And let's take a second to just gut check that this answer makes sense. And I'll do that. I'll rub off all the working out we've just done. Okay, so if you draw that quadratic, it will look something like this. Ooh. Gordon Bennett. I've got to get new pens, haven't I, guys? Anyway, if you draw that quadratic, it's got a positive coefficient, so it's going to be a U shape. And it's got a plus 3, so it's going to intercept the y-axis at positive 3. If you don't remember any of that, don't worry. Just graph this quadratic and you'll see that I'm right. So anyway, you graph this quadratic and it looks something like that. Now, let's think about what the different tangent lines in the form y equals mx must look like. Well, there's kind of going to be one like this, and that corresponds to the gradient of 5. As you know, positive gradient lines look like this, right? And then it also makes sense that there'll be one coming like that, from there. And you can see that that's clearly also a very negative gradient, i.e. m equals -7. So our answer indeed makes physical sense, which is a nice little good confirmation that we're doing the right thing. Anyway, that was quite a long video, guys, and I apologize if I bored you at all, but this is quite an important topic in coordinate geometry, and there'll be a follow-up video covering harder questions to really get your teeth into it. Anyway, thank you very much for watching Maths with Hamblin, and I'll see you in the next one, guys. Bye!